Hey, what's going on, everyone? My name is Tyler and welcome to my channel. Today we're going to get started with a programming language series that I'm really excited to start implementing. So if you want to follow along, you just need to have Deno installed, or you can follow along in your own programming language and runtime of choice. However, the implementation will be different between runtimes. But in this series, we're going to actually be building a fully fledged programming language that'll have common structs such as closures, functions, higher order functions, while loops, if statements, logic, variables, assignments, and a whole bunch of things like that, and a basic standard library. With that, you'll be able to translate this language into your own thing, have your own syntax and features, and I'll show you along the way what all these things mean. So before we can get into the exciting things like that, we had to do usually the most arduous task, which is building the lexer. So the lexer is simple in theory, it's kind of annoying. And to give a quick demonstration, if we have some source code like let x equals 45, which is valid JavaScript, we want to be able to translate this into an array of what we call tokens. A token is just something that a machine can give semantic meaning to. So let x equals 45 would then be returned in our language, would be turned into an array like this. A let token, an identifier token, which would have the value x stored inside it, an equals token, and a number token. So by the end of this video, you'll know how to create a lexer for our language, so that way in the next video, we can actually start parsing it and building this beautiful abstract syntax tree. So let's get started. First thing I'm going to want to do is I'm going to want to define, I'm going to export it first, but I'm going to define an interface for our tokens. So we're going to define interface token, and we're going to define what a token is. Well, as you can see up here, a token may contain a value in the case of x or 45, but let doesn't really have a value. Neither does the equals token. But for our simplicity's sake, we'll say every token has a string value, and every token needs to have a type. So we're going to say the type is of token type. Now token type doesn't exist, so let's go ahead and create this. I'm going to do exports enum token type, and we're going to say a token type is going to contain certain types of tokens. So let's kind of go over this and say, okay, what type of tokens do we have here? Well, we have a number, an equal, an identifier, and a let. Let's start with those. So we'll have a number. We have an identifier, right? It looks like we have a equals, a let, and that seems to be it. However, there are different types of tokens. For example, imagine if we added plus, and then a left parenthesis and did foo times bar. Now we have to account for an open paren token and a close paren token, as well as the plus and multiplication tokens we're going to want to be able to handle as well. So for now, I'm just going to kind of group these together into their own token. And we're going to call this token a binary operator token. So binary operator, because that's what they are. They're binary operations, meaning a left-hand side and a right-hand side, and an operator. So for now, this is going to be all of the tokens we'll support in our language. In the future, we'll have plenty more tokens, but for now, this is a good starting point. So let's actually get started now in parsing a string like this one into actual text. So let's get started by actually creating a function called tokenize, which means we're just going to take in a source, and I'm going to call it src, which is a string. Actually, I'll call it sourc. So we'll take in a source code and return a token array, just like this. So we're going to return an array of tokens, like that. So if we go up, we can create our array of tokens. Let's call it tokens is equal to a new array, like so. And the return type is going to be like so. There we go. So our goal is to take in a string. For example, this might be our source code, and return an array of tokens. So let's actually get started. I'm going to rename this from src or source to down here. We're going to call it const src is equal to source code. And what we're going to do is we're going to split on every single character. We want to get it so every single character has its own element in this array. So now we can actually read through this character by character. And what we're going to want to do is while we want to read in every single character in this input. So while src.length is greater than 0, we're going to continue parsing the tokens. So build each token until end of file. And there we go. So what we're going to do is for every single character in this array, we're going to continually build tokens. And then once we've built a token that uses some characters, we'll actually remove them from the array. Now, I am going to note this isn't the most memory efficient or performant way of doing this. However, it is the simplest way to explain. But in the future, if you're actually doing this and you want to make a serious lexer, you'll want to do a lot more work in actually making sure that you're not bleeding memory like we are here. For our case, it's more than fine. For a production parser, less than fine. So let's actually get started now and see how we're going to use this to build tokens. So let's say, first things first, let's see if we want to build a token for this left paren and right paren. So what I'm going to do is I'm going to do if source of 0, right? Because this is an array of each character basically. So if the first character is equal to a left paren, let's say now I want to actually build a left paren token. One thing I could do is I could do tokens.push, and then I would have to create an object, right, of type, and I would have to give it a token type.open paren, and then the value would have to be source.shift, like so. However, this is really ugly, and it's hard to read. Plus, a value technically could be undefined. However, we know it isn't. So I'm going to create a function that creates a token given these two fields. So we're just going to call it token. And we're going to pass in source.shift as well as the token type. So in this case, a left paren token is a token type of open paren. So token type.open paren, like so. And there we go. So now let's create this token array, or token function, sorry. Function token, which takes in the cars, or let's call it value, is a string, and it takes in the token, or no, the type, which is a token type, like so. And it returns a token. There we go. So now let's go ahead and actually basically create this function so it does what we want. All we're going to do is we're just going to return a token. So we're going to do value and type, like so. There we go. Now, one thing you'll notice is we're still getting an error here. Now, this is a TypeScript thing. It's because shift returns string or undefined. However, because of this line right here, we know that for a fact there is a value at index 0. So what we're going to do is we're just going to say instead of it being a string, we'll just give it a default value. It'll never use this, but we'll still give it to it, just so we don't have to worry about the types. And there we go. Now we've handled our left paren. Let's also now handle our right paren. So we'll do else if source of 0 is equal to a closing paren. We'll do close paren, just like so. And there we go. Now we've handled already 2 of our token types. However, there still are a few more we need to handle. For example, we're going to need to handle the binary operations. So else if source of 0 is equal to a plus, or source of 0 is equal to a minus, we're going to need to push back a binary operator token. So we're going to keep the shift. However, instead, we're going to change this to binary operator. Let's also handle multiplication and division tokens, like so. So we'll do source 0, same thing, source 0, and this will be a binary operator. We could also just combine these into their own type right here, and now we can handle all those like that. So now we've handled these 3 tokens. Maybe we want to also handle an equals token. So let's add the support for that. Else if source of 0 is equal to equals, then we're going to do our tokens.push, and so we're going to do dot equals like so. There we go. So now we can handle a whole bunch of different token types. The only things we haven't covered are numbers, identifiers, and lets. For this video, we're just going to go ahead and implement these, but it'll be a while till we actually use the identifier and the lets token. But let's get started. So down here, we know that if we make it here, that it's not any of these tokens, which means it must be either a white space, a new line, or something that we haven't covered yet. So let's go down here and type else, like so. So this is going to handle multi-character tokens, right? So tokens that are more than one character. Like plus is just a single character token. However, something like less than equals would be a multi-character token, or an arrow operator, or something like let is a multi-character token. So now what we're going to want to do is define a few functions that help us determine what type of tokens they are. We could use regular expressions. However, I know some languages have pretty poor support for regular expressions. So throughout this series, we're not going to use any libraries or anything that your standard language shouldn't contain on its own. So we're going to create our own function called isAlpha. And all this is going to do is take in a source, which is a string, and it's going to return whether or not this string is alphabetic in nature, right? So to do this, we're going to do if string dot, no, if src, sorry, dot to uppercase is not equal to src dot to lowercase. Not locale lowercase, just lowercase. Now, what this is doing is it's saying, okay, we know that the only characters that should be different if you call 2 uppercase and 2 lowercase on them are alphabetic characters, A through Z. Therefore, if we can convert both of them, and if they're different, they have to be alphabetic. If not, then they're not, right? Converting a decimal point to lowercase or uppercase doesn't do anything. So that's all we're going to do. We're going to check if they're alphanumeric by doing this, or alphabetic, sorry. To check if something is an integer or a numeric, we're just going to do function isInt. It's going to, again, take in the string. And what we're going to do is we need to know what the character codes are for numbers. So we're going to get C, which is the character in here. So we're going to do str.char codet, which is going to return the Unicode value of this character at index 0, which again, we're only dealing with one character at a time, so this is fine. Then we need to know what the bounds are for all of the other characters, right? We need to know that A, for example, is, I'm pretty sure, like 60 something. So we need to know if this character is in the bounds of 0 through 9. So we're going to do const bounds is equal to an array, and we're going to do 0.char codet 0, comma 9. Char code at 0. And this is going to return basically a tuple of the Unicode characters for 0 and 9. And all we're going to do is we're just going to return the if condition. So if C is greater than or equal to bounds of 0 and C is less than or equal to bounds of 1. And all this is going to do is it's going to say, hey, is the character C, is it greater than or equal to the Unicode index for 0? And is it less than the Unicode index of 9? And that'll tell us whether this is a numeric character. Again, there's probably simpler ways of doing this in your language. Some languages have it really simple. Some, you might want to write this. So we're just going to do it the slow approach for all of this. And so there we go. So now we have the ability to determine whether a function or a character, is of a certain type. So now let's actually use this. So we're going to say if is int, and we're going to pass in source at 0. So we're going to build number token. So what we want to do is we're just going to do let num is equal to string, and we're just going to do while. We're just going to do while the source dot length is greater than 0, and while is int of source at index 0. So while we continue hitting numeric values, we're just going to do num plus equals source dot shift, like so. Which shift in JavaScript just removes the first element of the array and returns it back. So we're just going to continually append the string of our number. And then all we have to do is just do tokens dot push, and we're going to push the token of token. So the value is num in this case, and the type is token type dot number, like so. And there we go. Next, we're going to handle if we find a identifier token. So else if is alpha of src of 0. So this is going to tell us if we found a identifier token. So we do the exact same thing actually. We build out an identifier token. So instead of num, this is going to be our ident, like so, ident. And instead of is int, we need to do is alpha, like so. And when we pass the token, we pass an identifier token, and we say the token type is of identifier. Now, there's still a few things we need to do with this. An identifier token could be something like foo, or it could be something like let. However, we need to determine whether this is a user-defined token, like foo, or a keyword that's reserved, like let. And to do that, I'm going to go up top and create a type that's going to basically hold on to all of our reserved keywords. So I'm going to come up here and call it keywords is equal to, actually we're going to give it a type first. We're going to say it's a record of type string, comma, string, or no, string, common token type. There we go. Now, what this is basically saying is this is just a dictionary. That's all this is, for those of you not using TypeScript. And what we're going to do is we're going to say the let keyword goes with the token type dot let, like so. And that's it. We're just basically defining a map for this keyword, like so. So now, all we have to do is down here, while we're creating the token, before we actually push a new token to the array, we want to check for reserved keywords. And we're just going to do const reserved is equal to keywords of, and we're going to pass in our identifier that we just created right here, right? So in this case, if they pass in foo, this is going to be undefined right here. So we just say if reserved is equal to undefined, then we call this right here. It's an identifier. It's not something that we know about. However, if it isn't undefined, then reserved is going to contain the token type that was there. So all we have to do is push this token like so. And instead of the token type being that, it's going to be of type reserved, like so, which is again a token type. So we're checking for reserved keywords. We're basically indexing the hash map at the identifier value. If it exists, it's going to return a value like token type let or token type while, etc., right? But if it doesn't exist, this is going to return undefined, aka it's something we don't know about. It's a user-defined keyword. And that's it. So this is how we handle numbers. This is how we handle alphabetic characters. And what we're going to do is we're going to create one last function for determining skippable characters. So function is skippable, and it's going to take in the string, and we're just going to return if str is equal to a white space or is equal to a new line, or str is equal to a \t for a tab. That's it. Is skippable. We don't really care about these tokens, the strings, white spaces. We don't care about new lines, and we don't care about tabs. So we're just going to get rid of them. There are better ways of doing this, but again, we don't really care about the most optimal solutions. We're just trying to get a working programming language, and in the future, if we need to come back to this, we will. So that is almost it. So now, at the end of our is_int and our is_alpha, we can do else if is skippable of source 0. We can just do source.shift, like so. And this is just going to skip the character. However, we do want to be able to handle characters that we haven't determined. So we're just going to do a console.log unrecognized character found in source. And let's just say, let's pass the source at 0. And then I'm just going to do deno.exits, which is going to cancel the execution, and we're just going to exit right now. In the future, we might talk about how to do soft error checking, how we can possibly recover from this, but this is an unrecoverable error for now. So that is pretty much it. To recap, we create a tokenized function that takes in a string of source code and returns a token array. Then we define the array, we split the tokens, or the string, so every character is in its own cell, and we loop through every single character by character until there's no more. If a character matches a known token, we create a token for it. If it doesn't, we throw an error, and if it's something that's skippable or user defines, like a number, an identifier, or a keyword, then we handle them in their own functions respectively right here. So that is basically it for our lexer. Let's quickly go ahead and actually test this out now and just make sure that this works. So we have our tokenized function. Let's come down here and do const tokens. Actually, let's just do a for loop. So for const token of, and we're going to do tokenize, and so we're going to pass in our source code. Like so. And I'm going to create that const source is equal to awaits deno.read text file. And we're just going to read our current file, lexer.ts. So that's all this is going to do, is it's just going to read the file into a string and print back every single token. And I'm just going to do console.log token, like so. And now, hopefully when we run this, we'll see that we get back tokens for all of this stuff right here. So let's actually go ahead and test this out. Let's open up VS Code. I'm going to move this to the right-hand side, close that, and let's just do deno run -a and lexer.ts. Unrecognized character found in source. So that is something that we will need to be able to handle, right? Else console.long source of 0. Oh, yeah, there's a lot of characters in the Deno source code that it can't handle. Like, for example, brackets, things like that. So let's create a file for testing. So we'll just call it test.txt. And in here, we'll just say, let's x equal 45. We should be able to parse this. So now let's rerun this and instead pass in ./test.txt. Hey, and there we go. So if we clear and rerun it, we get value of let. The type is 6 because that's our enum type. So we can see this is the 6th type. We get x, which is type of 1, which is different. identifier is 1, right? If we change this to let like that, they would both be of type 1. However, we're saying that this is a reserved keyword. So when we run this, we get type 6. Equals is of type 2, which is correct. And 45, it was able to parse out the number, is of type 0, which is a number. Let's now try a more complex string, like 45 times 4 divided by 3. There we go. And hopefully now we will be able to handle the plus, the division, the multiply, and the open and close parenthesis. So let's try this out. And it looks correct. Let, cool, x equals 45 times an open paren, a 4 divided by 3, and a closed paren. So that looks awesome. If we had a token like a semicolon, however, we can see in our error, unrecognized character found in source, and it's a semicolon. So that's exactly what we want. We have now been able to transform a sequence of characters into recognizable tokens. This may not sound really impressive or really exciting, but you'll see really quickly in the next episode when we start our parser how this is a really important step. And it is a really annoying step. We simplified over a lot of things. We didn't use regular expressions, though those can severely speed up this process. But yes, we were able to parse a string of tokens. In the next video, we'll actually get started by translating this tokens array right here into a actual AST expression tree that'll represent the actual semantic meaning of this code. So we'll have a tree that will allow us to work with code like this, and it'll respect the order of operations as well as grouping operators like such. So I'll see you guys in the next video.